Hi everyone, I'm Jinghua Liu. I will introduce our paper, Generating API Parameter Security Rules with Large Language Model for API Misuse Detection. This work is done with Yi Yang, Kai Chen, and Miaoqian Lin, and all of us are from Institute of Information Engineering, Chinese Academy of Sciences. As we all know, application programming interfaces are widely used in software development, and APIs can accelerate the development process and offer functionalities and offer diverse functionalities. However, developers may not know the implementation details of APIs. They may violate security rules and cause security issues. For example, users should release the second parameter of circular open, but the code below fails to close it after calling this API and cause a memory leak. So how to detect API misuse caused by incorrect parameter use like this? First, we should understand the API parameter security rules, or APSRs, and then detect the violations of APSRs. Previous work generated APSRs by analyzing different types of data. Some studies extract APSRs from API documents and API calling code. However, they are limited by the resources they rely on, leading to incorrect APSRs or missing APSRs. And API source code is a good resource because it can directly reflect the API behaviors. Some studies analyze it to generate APSRs. However, they rely on predefined code analysis rules, which limits their scope. Large language model, or LLM, which is a new and innovative technology, can analyze code without predefined code analysis rules. Therefore, we explore to use the LLM to analyze API source code and generate APSRs. There are some challenges to finish this. The first challenge is the LLM may generate incorrect APSRs, lead to incorrect misuse detection. For example, when we instruct the LLM to generate APSRs for the free API, it may answer, the parameter must not be null. However, passing a null pointer to the free API won't cause security issues. If we directly use this APSR to detect violations, it may cause many false positives. And the second challenge is APSRs generated by LLM may be too general to be translated into detection code. For example, an APSR generated by LLM is parameter 2 must be a valid pointer. Here, the valid is quite vague, and different people may have different interpretations to it. In this context, only the first interpretation, must not be null, is correct. Such ambiguities will cause incorrect results. We address these challenges based on some observation. First, we observe that if a code violates a correct APSR, it often causes runtime errors. For example, the code on the left violates the APSR that parameter must not be null, but runs successfully, indicating this APSR is incorrect. And the code on the right causes a double free error, indicating the APSR about double free is correct. Based on this, we propose the execution feedback checking method to validate the correctness of the results from LLM, solving the challenge 1. Additionally, code as a formal language can express more concrete information than natural language. As the figure shows, we can analyze these two codes and identify that API misuse is related to the null pointer. And by describing this code, we can generate a concrete APSR. Parameter 2 must not be null. Based on this, we propose a method that instructs the LLM to analyze the code and generate concrete APSRs based on the code, solving the challenge 2. Based on these insights, we designed GPT-8, a framework that uses LLMs to generate APSRs and detect API misuse. I will first introduce an overview of GPT-8, which consists of 4 stages. Stage 1 is raw APSRs generation. GPT-8 instructs the LLM to analyze the API source code and generate raw APSRs. Stage 2 is APSR validation. GPT-8 validates the correctness of raw APSRs based on execution feedback checking method. Stage 3 is APSR refinement. GPT-8 guides the LLM to generate the concrete APSRs by describing key operations. Stage 4 is API misuse detection. GPT-8 detects violations of APSRs. We then use some examples to introduce the detail. In stage 1, since APIs can have many parameters and code, analyzing everything at once may reduce the effectiveness. To address this, GPT-8 splits the task, instructing the LLM to generate APSRs for one parameter at a time. For example, for the API pcap dump with 3 parameters, GPT-8 breaks down the generation task into 3 subtasks. And for each subtask, GPT-8 provides API source code and instructions, then instruct the LLM to generate raw APSRs. And in stage 2, GPT-8 validates the correctness of raw APSRs based on execution feedback checking method. However, this is not always straightforward. Considering the raw APSR of circular 3 open, parameter 1 must be an existing database file, and the violation code is shown below. An error occurs during execution. Does this mean this raw APSR is correct? By analyzing this code, we can identify that the second parameter of circular 3 open is null, which may cause null pointer dereference, and this error is not related to the raw APSR. Therefore, this runtime error cannot be used to prove that the raw APSR is correct. So how to automatically determine if the code only violates the target APSRs? To address this, GPT-8 first generates the write code that calls the target API successfully, and then GPT-8 modifies the write code to generate the violation code. Finally, GPT-8 performs a cross check based on predefined rules to compare the code changes against APSRs, ensuring consistency. The details of the predefined rules can be found in the paper, and I will introduce the details of write code generation and violation code generation. To generate a write code, GPT-8 provides API source code and instructions, and in this process, to improve the success rate, if a code cannot run successfully, GPT-8 provides the execution results and the code, then instructs the LLM to fix the code. To generate the violation code, GPT-8 provides the write code, raw APSRs, and instructions to the LLM. For example, for the raw APSRs, parameter must not be null. The violation code generated by LLM is shown on the left, and it runs successfully, indicating this raw APSR is incorrect. And for raw APSRs, parameter must be valid. The code generated is shown on the right. It caused a double-free error, indicating this raw APSR is correct. And in stage 3, GPT-8 instructs the LLM to identify key operations based on code differential analysis and generate concrete APSRs by describing the key operation that caused this bug. However, as the figure shows, code changes may contain many operations. Failing to identify the key operations may lead to incorrect APSRs. So how to identify the key operations? We observe that bugs caused by similar key operations always cause the same runtime error. As the figure shows, there are 2 violation codes and they have the same execution result. By analyzing this, we can identify a common operation, which is the key operation causing the runtime error. Based on this observation, GPT-8 first clusters code with the same runtime error messages and guides the LLM to analyze their common operations to identify the key operations. To assist the LLM in identifying the key operations, GPT-8 provides runtime errors in the prompt. And there are slight differences in the prompt when a group only contains 1 violation code. For more details, please refer to the paper. As the figure shows, GPT-8 guides the LLM to analyze all the inputs step by step and then generate the APSR. The final APSR must not be null. It's more concrete than the raw APSR. To detect the API misuse, we adopt the approach proposed by previous work advance. We manually analyzed the APSRs, identified frequently occurring patterns, and created detection code templates for each pattern. GPT-8 then automatically combines these templates to generate the final detection code for performing the detection. We evaluated GPT-8 on 8 popular libraries, and the results show that GPT-8 generated 8 types of APSRs with a precision of 92.3%. GPT-8 detected 210 new misuse and generated 355 new APSRs. We also compared GPT-8 with 3 state-of-the-art approaches, and the results show that GPT-8 covers more APSRs and bugs. We summarized some lessons for prompt design. First, insufficient information caused fabrication. When the task results appeared fabricated, providing additional information can be helpful. And the second lesson is the examples may be harmful. The examples in the prompt may limit the LLM's ability. For example, when we instruct the LLM to generate APSRs, if we provide an example output with some APSRs, the LLM tends to repeat those in the example output while ignoring others. In conclusion, we proposed GPT-8, which is a novel approach to generate accurate and concrete APSRs using LLM. And GPT-8 detected 210 new bugs and generated 355 new APSRs. We also provide valuable suggestions on prompt design, and our code will be available soon on GitHub. Thank you for your attention.
Okay, so I have a first question again, but please, if you want to ask a question, come to the mic. Can you go back a few slides to your comparison with other prior tools?
Yes.
Yeah. So how many of the bugs that you found here are the same as the bugs that the other tools find? Do you find the same? Are the 99 here all in your set of 243, or are they all different, or how do they overlap?
I don't know the exactly data, but yes, there's some bugs that GPT-8 can't find.
Okay. And those are bugs that maybe another tool, so maybe if you applied Advanced and GPT-8 together, you'd find 260 bugs or something like that. Or something like that, where you'd find a few extra, right? Does that make sense?
Sorry?
So Advanced might find some bugs that you don't find,
yes.
and you find obviously lots of bugs that they don't find.
Yes.
But, okay, all right. And then one other related question is, a lot of times memory corruption can be silent and only be triggered later. And in fact, when that happens, a lot of times the way in which the memory corruption is evident is different because something has been corrupted and different things might get corrupted on different runs. Mm-hmm. How does GPT-8 deal with a situation like that?
Well, the memory corruption, for some time, if the bug can't cause the runtime error, and GPT-8 will miss these bugs. This is the limitation, and we will design more, maybe sanitizer to address this problem in the future.